You're already professional doing that.
No, but it doesn't seem to work. That's all.
Really?
Well, it says that it's on, but I don't. I'm not getting anything.
Wait a second. Okay. Sounds working.
Okay.
1, 2, 3, 4.
Maybe I put it too far.
Yeah. Seems like it's gonna be the last one. Can we change the batteries?
Okay. Okay. It's not clear to me that this is working. Maybe you should change the battery.
It's not the batteries.
It's not the batteries? Okay. It's me. Is it better? Is the mic working? Okay. Okay, cool. Okay, all right, okay, thanks. Well, right, but no one, they're not. Okay, I guess I'll assume it's fine, and if it's not fine, you should speak loud. And okay, so I'll restart where we were yesterday. So for this lecture, we're going to talk about random circuit sampling. So I'll define it as a verification task of the kind that we described last time, and then I'll give some of the arguments that go behind the soundness of that task. So I already described last time what the Google experiment was. So this is like the kind of like concrete experiment that was done. They took 53 qubits, arranged on a 2D grid. So 53 is not quite a square, so there were some holes. And then they ran the depth 2 nearest neighbor, a depth 20 nearest neighbor circuit. Repeated this like some million times and collected at each time you measure the output, you collect all these outputs, and then you compute some score of the outputs that I'll talk about later. Let's use a proxy for a second. So instead of analyzing that specific test, I'll analyze a slightly derived test, which is easier easier to talk about. So the task is almost the same. So the input is a description of a circuit. The output is a string y, and success in the test is measured in total variation distance. So total variation distance is the statistical distance between two distributions. One is the ideal distribution, the one that's written on the right. It's the outcome distribution of the circuit. And another, py, this is the probability that whatever device I'm running the test with returns the outcome y. So in general, I cannot compute py because I just run the test and I get a certain y. If I run it many times, I could estimate py. But in general, I cannot compute it. This is why this is kind of a proxy. Okay, so I'm just assuming that I have a way to access this quantity, and I'll say that the device succeeds in the test if it achieves a bound here. So epsilon is maybe 0.1 or 0.01, something like this. Okay. So the first claim is that it's easy, or at least not too hard, to succeed in this task using a quantum computer. Okay, you just run the circuit, you get a y. The output distribution of the computer, if the computer has no noise at all, is going to be exactly the correct output distribution. So it'll, left-hand side will just be 0, which is less than epsilon. Now, if the computer is noisy, if there's really a small amount of noise, this will affect the output distribution a little bit, and you hope that the total variation distance will still be less than epsilon. Unfortunately, this requires a really low noise level because noise is additive. So if you have some small constant noise per gate, now that I'm doing something like 50 times or maybe 20, something like 400 gates, if the noise would need to be significantly below 1 by 400, which is not in the Google experiment. So the Google experiment by this metric fails, and this is why they're using a proxy quantity there. But let's just assume that we have a noiseless computer. In this case, we can succeed easily in the task. Okay, so that's the concrete completeness for that particular task. Now, the part that's interesting is arguing about soundness. So why is it the case that sampling from the outcome distribution of a random circuit is hard? And this is what I want to talk about in this lecture. So first, if you've never thought about this, you could think, well, come on, like this is a random circuit. So what's the output distribution going to look like? Random, right? So how hard can it be to sample from a random distribution? So you could have a distribution that's like this. So I'll plot the possible outputs y. So each dot on my x-axis is an output, and this is their distribution, py. And the uniform distribution looks something like this. Okay, the number of y's, there's 2 to the n of them. If I say that I have n qubits, and this would be 1 over 2 to the n. Okay. So sampling from that distribution is really easy. And so if that was the output distribution of a random circuit, then this experiment would be very easy to spoof. The point is that it's not. So if you take a very, very shallow circuit, for example, if my circuit is, these are the qubits, and then my architecture is I just have a single layer of single qubit gates, okay? And these single qubit gates are chosen at random. They're either the identity gate or they're sigma x gate, okay? If I run a random circuit of that form and I initialize the input to 0, then what's the output going to be? Well, if I put the identity, it's going to be the same. If I put sigma x, it's going to be flipped, so I'll get a uniformly random strain. So a random circuit from that family of circuits generates this output distribution, and that's really easy to spoof. Now, if you take circuits that have a slightly higher depth at least logarithmic in the number of qubits, then the output distribution doesn't look like this at all. You can do the calculation, so as the depth increases...
So you average over the different circuits?
No, I fix the circuit. So this is the typical output distribution. Sorry, no, oh, you're right, so sorry. Yeah, this was wrong. I should put Hadamard gates. I'm sorry. They should be Hadamard gates, and then no, this should be the output distribution of a single circuit. Thanks. Sorry. So it's not going to look like this at all. It's going to be an exponential distribution. So it's going to look something like this, where in general it would be something like that, but I reordered the outputs y according to most likely. So this is not the old 0 string. It's just the most likely y for that particular circuit, and then it goes like this, and this is py. Right. So this is. Right, so for this family of circuits, you're generally going to observe something like that, or something even worse, even simpler to fake. If you choose circuits that have 2 qubit gates and that are deep enough, then they're going to implement a unitary that approaches, in some metric, a uniformly random unitary. And if you were to implement a uniformly random unitary and measure the output and plot what the output distribution is, it's not uniform. It's something that looks like this. It's like concentration of measure, or if you take a random state on the unit sphere, and you measure it in the standard basis, then the outcomes will not be uniformly random. There will be some that are more likely and some that are less likely. It's a very simple calculation in like high-dimensional geometry, but it's not. You could say that it's due to entanglement if you want. If you want like a physical explanation. If I take a circuit that's like this, that has single qubit tensor gates, then the output is just going to be very simple, and the distribution, the probability of a certain string will be the probability of the first bit times the probability of the second bit times the probability of the third bit. As you add depth and you add 2 qubit gates, I get a state that's more complicated. That's a superposition, and this superposition is in general not going to have uniform coefficients. They have coefficients that are distributed according to Gaussians, and if I take the square of these Gaussians, I get the exponential distribution. It's a simple calculation. It's not a deep fact. Well, no, you didn't try, right? So if you try, you can do it. You just didn't try. So, okay, but so just to go back to the experiment, this is what we're trying to verify, right? So the quantum computer is supposed to generate outputs y's that have this kind of distribution, and there's always going to be one of the outputs that's more likely than the others, and then some that are a bit less likely, and some that are very less likely. And so if you want to spoof the experiment, what you're trying to do is to figure out which y's are more likely, which y's are less likely, and then you're trying to generate some of the more likely y's more often than the least likely y's. This is what the classical procedure trying to fake the experiment would be trying to do. Yeah?
So the next question is, one property, or if I just randomly pick a classical circuit and just look it out, would it be uniform?
Well, if it's a fixed classical circuit, you choose the circuit at random. So here, this was the point made by Itai. What we're doing is that we're choosing a circuit at random from some class of circuits, and then we're fixing the circuit, and then we're running it, and we're asking what outputs do we see. So if you take a random classical circuit, you fix it and you run it, it's always going to return the same thing. So the distribution, it'll look like, it'll return something. It'll look like, this is what it'll look like. And I'm just running it many times and we're looking at the outputs. Yeah. What we want to argue is that sampling from this distribution is hard. But we're going to take a little bit of a detour. What we're going to try to argue is something a little bit simpler, which is that if you were to try to compute the probabilities, then this would be a hard task. Okay, that's the first step. If someone was able to compute the probabilities, then they could just use a random number generator and tune it to these probabilities and sample it from the distribution. The intuition is the Feynman path integral. I mean, what's the natural way to compute this probability? You can express the probability as a path integral. So you go through the circuit, you introduce resolutions of the identity at each layer of the circuit. If you've never seen this before, I'm not explaining it in detail. The point is that you can express this squared probability as the square of an exponentially large sum, and each of the terms in the sum represents the amplitude of a particular path in your circuit. In particular, because it's a quantum circuit, this can be a negative number. In fact, in general, it's a complex number. The idea is that if you trying to approximate or even compute an exponentially large sum when the terms inside the sum are signed or are complex, this is subject to cancellations, and we just don't have a good method for doing this. To compute or estimate exponentially large sums, you can use Monte Carlo sampling methods, but these work when the sums add themselves. When there can be cancellations, it's very hard to detect these cancellations. Okay, so the intuition is, okay, this is what I'm trying to compute. It's an exponentially large sum. It's signed. I just don't know how to do it. So it's probably going to be hard. Okay, so let's try to go a little bit beyond that. So I'm going to make a little bit of a detour through some basics of complexity theory, but it'll be short. So I'm going to introduce a class of problems here. Okay, so this is a little bit of an aside, and then we'll return to what I was talking about after. Yeah.
So, because my idea of comparing to experiments, because it said there could be some consequences of, like, there could be some evidence that's classically.
Yeah. Yeah.
So your evidence is that you don't know.
No. This was the starting point. We're going to do better. We're going to do better. It's only like 15 minutes in, so I have half an hour. So, so let's do better. Exactly. So. Okay, so I'm defining here two different computational problems. The first one I call sharp P, the second one I call gap P. These are names of complexity classes, but it doesn't matter too much. So in the first computational problem, you're given access to a function. This function maps n-bit strings to bits. And what I mean by you're given access to a function, you're given like a formula for the function, and it's easy for you to evaluate this function on any point. Okay, so if you want to compute f of 0, you can do it, f of 1, you can do it. But your task is to sum the function over all possible inputs. Okay, that's the problem of the first kind. Problem of the second kind, same thing, except the function is takes values in -1, 1. So it's the set -1, 1. And again, you want to sum the values of the function. Okay, so how hard can that be? For the first problem, think that f could be like a 3-stat formula, and summing. So f says whether x is an assignment to the formula, and f says whether x satisfies the formula or not. So summing f of x is counting the number of assignments to a 3-stat formula. Already deciding if the formula has one satisfying assignment or not, that's NP hard, because 3-stat is NP hard. Counting the number of satisfying assignments is much harder. So this is an extremely hard problem because basically it's an exponential sum, so in general it's just going to take you exponential time. That's the first problem. The second problem, how hard is that? I mean, it's the same, right? Like summing some 0, 1 values or summing some -1, 1 values, if you want to compute exactly the sum, it's exactly the same thing. I could take my g and then I replace it by g plus 1 over 2 or something like that, and then I get a function of the type f, and then I can switch between the two problems. So same complexity. So there's actually no difference between summing a lot of 0, 1 values or summing a lot of -1 values in the complexity. Okay. Now something more interesting is going to happen. Let's talk about approximations, okay? Because in the end, in the problem that we're considering, this function g is going to be something like the amplitude along a path, and no one's computing that, right? Not the quantum computer is not computing it either. It's just sampling. So let's relax a little bit and let's talk about approximation. Okay, so how hard can it be to find an approximation to the sum up to a factor 2? Let's say 2 is kind of arbitrary. These are worst case problems. I'll talk about that. Yeah, I'll talk about that a little bit later. Yeah. Here in general, we're talking for an arbitrary worst case function. Nevertheless, so for an arbitrary worst case function, it turns out that for the first case, for sharp P functions, approximating the sum to a factor 2 becomes easy. So in complexity theoretic language, the complexity goes down to BPP to the NP, but I don't want to explain what that means. So just think that it's easy. I mean, it's not trivial. There's no randomized algorithm. You need something a little bit more complicated than a randomized algorithm, but it's much easier than computing the sum. It's provably much easier. No, not provably. It's much easier than computing the sum. The intuition is that you're going to be able to approximate it by sampling. So I don't want to explain that a little bit because it's actually not that straightforward. But there is an idea that dates to the 70s. There's an algorithm that dates to the 70s that lets you approximate the sum to a factor 2 much faster than computing the exact sum. Okay? Now there's a difference with the second case. For gap P functions, it turns out that approximating the sum to within a factor 2 is just as hard as exactly computing the sum. This you can actually prove in your heads. It's basically just by binary search. The idea is that suppose that you were able to approximate the sum to a factor 2, and now I want to compute it exactly. The first thing that I'll do is I'll try to determine if the sum is positive or not, okay? So I run my algorithm, and by the thing there, you know, if the sum is positive, it should return an A that's positive. If the sum is negative, it should return an A that's negative. So it's telling me if the sum is positive or negative. Let's say it was positive. The largest it could be is 2 to the n, okay? So let's try to decide if it's bigger than 2 to the n minus 1 or less than 2 to the n minus 1. I'm going to shift the function a little bit by 2 to the n minus 1, and then again ask my approximation algorithm, okay, now that I shifted it, is it bigger, is it positive, or is it negative, etc. You do binary search. So this shifting doesn't preserve that it's a minus 1, 1 function, but you can do it in a way that preserves, okay? So I'm not getting into the details. Okay, so the lesson that we learned from this is that exponential sums of 0, 1 or minus 1, 1 functions are just as hard to calculate, each of them, but if I allow multiplicative approximation, then there's a difference. Okay? And we're going to try to leverage that difference in order to show that no classical, okay, in order to show something, which I'll show on the board. Okay, so there's a consequence. So the consequence is, suppose that there exists a classical randomized algorithm, let's call it A, that samples some strings y with probability py such that py is a factor 2 approximation. Well, let's say I'll be a little bit looser, sorry. So, okay. Let's say it's such that py is a factor 2 approximation to the correct value. No. Okay. I want to argue that that's highly implausible. There's some caveats to that. We won't be done once I've argued that this is highly implausible. For example, because as Eddie pointed out, here I'm requiring the classical randomized algorithm to do this for every single circuit C, but to succeed in my test, I only need to be able to do it for a random C. Okay, so, but I'm just focusing on this particular statement, and I want to argue that this is very unlikely. Okay, so why is this very unlikely? So suppose that this was the case. Then I can define a function. So let's define a function fy of x, and this would be 1 if a using randomness x. So A is a randomized algorithm. One way to think about a randomized algorithm is actually a deterministic algorithm. So it's just a function, but it takes as input random bits. Okay? So here I think of x as the randomness that A uses. So I fix its randomness to x and I run it, and then it's going to say something. If it said y, then I define the function to be 1, and if it didn't say y, then I define the function to 0. So I can define one such function for each randomness returns y. Returns y. It does not return y. Okay, does not return y. Okay. Now, fy is a function. Okay, so I'll go back up. Fy is exactly a function of the type sharp p, right? It maps bit strings to bits. Okay, so I know by what's written over there that approximating the sum of these values there's an algorithm that's able to do that. It's an easy problem. So this implies by A, there is an algorithm. This algorithm is not quite a polynomial time algorithm. It's slower than that, but I'm being a little bit sloppy here. There is an algorithm B that returns a factor 2 approximation to the sum over x of fy of x, but this is exactly the probability that the algorithm returns y times 2 to the n, okay? 2 to the n times py. So by the assumption, 2 to the n times py is a factor 2 approximation to 2 to the n times the output probability of the circuit, okay? So what we've shown there is that if there exists a classical randomized algorithm that's able to do that, then there's another algorithm. This is a classical algorithm B. It's an efficient classical algorithm B that returns a factor 2 approximation to this, which is a factor 4 approximation to the output probability of the circuit, okay? So this was an assumption. The conclusion is that we have an algorithm that approximates up to a factor 4 the output this squared, okay? But now what is this? We've seen by the Feynman path integral thing is that this is actually, I can express this here. This is something that looks like the sum over, let's say I'll use another variable z of gy of z, and there's a square on the outside, where gy of z is what? Is the amplitude that's associated with the path z in the circuit. Gy is not quite plus minus 1 valued, it's valued in the complex numbers, but you can set things up in such a way that it's a plus 1 minus valued function. In particular, this algorithm B actually returns a factor 4 approximation to the sum. You can also ignore the squared, that's a technicality, to the sum of a gap P function. But we just wrote over there that approximating gap P functions should be hard. So then I have here, I have a contradiction with B. It's a particular one, yeah. So that's a good point. So in order for this to be a contradiction with B, I need, this is actually an important point, I need this specific gap P function to be among the hard ones, okay? And that's part of the argument. You need to show, if you want to apply this proof strategy to random circuit sampling, you need to show that for a random circuit, you're able to generate okay, there's another thing about random circuits, but for circuits of that architecture, circuits from that architecture generate functions, this function, that are among the hard class of gap P functions. And you can do that for the Google architecture, you can do that for QAOA, as Eddie mentioned, you can do that for boson sampling, you can do that for IQP. So this is one of the places in the argument where the class of circuits you're considering enters the picture. Okay, by contradiction with B, what I mean is that we've obtained an efficient algorithm that solves a hard problem. In general complexity theory, we still can't completely rule that out. So this contradiction, this is where a complexity theoretic assumption comes in. This is like, okay, assuming that hard problems exist in the first place. So ideally, I would write assuming P different from NP. Okay, it's not quite what I write. It's something a little bit more complicated. It's assuming polynomial hierarchy doesn't collapse. But that's like technical complexity theoretic lingo, which is slightly weaker than this. I'd prefer to write this, but it's morally equivalent. Okay, so let me just, this is the key of the argument. After that, there's more discussion, but that's the technical heart of the lecture. So it's the part that's useful to try to get. What we've been able to show is that if there was classical algorithms that approximated output probabilities of quantum circuits, this would basically mean that I have a way to represent what is a sum of signed amplitudes using a sum of non-signed numbers, which are the paths but of the randomized algorithm, which don't have signs. And I have complexity theoretic evidence that one approximation problem is much easier than the other, and so this just couldn't be the case. The summary so far is that we've argued that assuming P is different from NP, there is no efficient classical algorithm that returns Y with probability Py that is within a factor 2 of the output distribution of a circuit C. So there's many caveats. So maybe some people in the audience want to suggest caveats. Why am I not done? Why is that statement not enough to say that it's classically hard to succeed in the test that I introduced at the start of the lecture?
Maybe it's not just that quantum is easy?
No, so this we'll just accept. To do what? So, yeah, so that's one problem. So,
I think that it's complicated to actually sample random circuits by the armature.
No, that's not hard.
The gates doesn't mean that you sample from the uniform.
That's technical, but it's not part of the hardness. That's part of the completeness, and I'm assuming that my architecture allows me to implement uniformly random gates. You're right. In practice, there's going to be, I can't implement the exact gate that I want, so there's a little bit of fuzz there. But let's say that's okay. Let's leave that to the engineering department, and they're very good, and so it's fine. A related caveat maybe would be that this is not what the quantum algorithm is doing still, right? So maybe a first one is that even if you're able to implement exactly that circuit, the quantum algorithm doesn't return py that is, as soon as there's a tiny bit of noise, okay? If there's a tiny bit of noise, you're not going to preserve the probabilities up to a multiplicative factor 2. So multiplicative factor 2 is extremely stringent. I think that these probabilities are exponentially small numbers. Some of them are even smaller. So getting within a factor 2 approximation, that's extremely hard, and it's not something that you can verify. If you remember what I was aiming to verify earlier, in fact, I didn't define the test, but I defined an intermediate test, and the intermediate test was, this is what we were checking. Okay? This is much less stringent. In particular, this allows some of the PYs to deviate from, it could be that in a small number of cases, PY is 0, and this is positive, or this could be 0, and that's positive. Because both of them are anyways typically exponentially small, it doesn't contribute that much to the epsilon, okay? So this kind of criteria allows you to spread your error in different ways, and you have to be, overall kind of correct to some additive error, but you don't have to be correct for every single y, as this is requiring, okay? So that's a caveat. And here I've argued hardness of a task that not even the quantum computer can be expected to satisfy, unless it was really extremely perfect, but it's not going to be extremely perfect. Okay? What are other issues with my statement?
Raise an issue and you can solve it?
No, not yet. I'll solve it. I'll try to solve it after. There's a couple more issues that we could raise. Okay, one I'll just write it. This is what Eddie said. So far, the argument is worst case, and this is actually a very important point. These complexity theoretic arguments, when we say that a certain computational problem, solving 3-SAT, or computing an exponentially large sum is hard, we mean that there are some functions, there are some formulas for which it's hard to do that. Now, which formula? In general, we don't know how to answer that. It's just, okay, there is one that's hard, that's what we know, but we don't know which one. So here, same thing. So far, the argument says that there is some circuit such that solving this for every y is hard. But when I generate a random circuit, what's the chance that I get this particular one that's hard? Well, it could just be 0, right? Because there's a continuous space of circuits. So what we really want to argue is that this is hard for a random C, okay? We need average case. This is a step that's extremely difficult to get over in any kind of proposal that you guys might come up with for determining a quantum advantage, because everyone is telling me, okay, let's do this quantum simulation or this, etc. But then we really have to say, okay, but how did you choose the Hamiltonian, or how did you choose the circuit? And are you sure this one is hard? Because you just gave me one example, but how are you going to generate them in the test? And you need a family that you're really sure is hard. We haven't achieved that yet.
So if the circuit would be the circuit to try to sample state of an NFTS linear, then it might be a family that we consider as something that is in average case is also faster.
You could try. You need to have a distribution over an LTS Hamiltonians.
So basically, you know how to generate a family.
So if you know that, then you could try that. Yeah. Okay, so we're going to try to solve. I'll be a little bit more loose, but I'll try to explain how both of the caveats can be solved at the same time, okay? One of the caveats was okay, but this like multiplicative approximation that's way too stringent a criterion, no one can be expected to satisfy it. That's caveat number one. Caveat number two, okay, but anyways, it's only hard for worst case C's, and I don't know how to generate a worst case C. I only know how to generate a random C, or I have to say what's the distribution. Okay, so back to the slides. I rewrote here the goal. This is the same goal that was written before. And there's two important observations. Each of these that are needed in order to overcome the caveats. Each of these is like a technical result. So the first one is called average case to worst case reduction. And I'll say maybe a little bit more about that in a second. But the idea is to show, to boost a little bit what we've shown and to show that this is hard to solve, not only for worst case C, but also for random C. Actually, let me explain a little bit how to do that, and then I'll talk about the second steps. Okay, so how do we solve this first problem? You know that solving for worst case C, so this is given to you, and you know that it's going to be really hard to return these approximations for C in the worst case. You want to show that it's hard for a random C. The idea is to do a proof by contradiction. Suppose it was easy for random C's, but maybe not for this one that was given to me. I'm going to try to use the fact that it's easy for a random C in order to solve it for an arbitrary C. So what I'm going to do is I'm going to take this C. This is a worst case C, so it's really nothing special about it. It was someone handed it to me. And then I'm going to generate a bunch of other C's. So let's call them C prime 1, C prime T. These are other circuits, but such that two properties should hold, such that, first of all, each C prime I looks random, or is random. Okay? So that because it is random, and using my assumption by my proof by contradiction, I'll be able to solve that problem for any of them individually. And then second, given solutions, so given some, let's call them A prime Y I, which is a good approximation to the probability of that circuit C prime I returning Y. Okay, this is within factor 2. I have an algorithm, a classical efficient algorithm, to recover AY, which is a good approximation for my original circuit. Okay? If I've been able to do that, then I've shown that the worst case, that the average case is just as hard as the worst case, because I can solve the worst case by solving the average case. Okay, I map the worst case circuit to some random circuit. I solve the problem on the random circuit, and also I have a way to go back, use the solution for the random circuits to recover. Okay, so how do we do? Yeah?
Do the CIs look random marginally or
Marginally. But that's enough, because the algorithm that I'm assuming might exist for a random C prime, it's just sitting there, and I can just tell it, please do it for C prime 1. And then, maybe I like erase the memory and then do it again. These are classical algorithms, so yeah. C is the first one, and these are different. So how do we do that? I'll just like sketch the one possible idea. There's different ways you could think of doing it. So let's take our circuit C, and okay, I'll just do it for the case of a single gate, single qubit circuit for simplicity, but you can easily generalize this. So this is some gate, U, and it's the gate that comes from C, so it's really arbitrary. So now let me construct new circuits as follows. So I'll add here two gates that cancel each other. Sorry, I'll add, no. I'm sorry. I'll add a gate here, and what gate am I going to add? Something like e to the I, T, H, where H is randomly chosen Hermitian. So this is C prime. Oh, there's too many I's on the picture. Okay, let's call this C prime T. Okay, for every real value of T, I can define a new circuit C prime T, which is the old circuit, but after that, there's just a random unitary, okay? This random unitary, they're related between the different C primes, but by themselves, this is just a random gate, okay? So C prime 1, C prime 2, in fact, C prime T for any T that's not 0, okay? If T is 0, this is the identity gate, I get C. That's not random. But any t that's positive, this is just going to look random, it's going to absorb the u, and overall I have something that, that looks random. Particularly for t equals 1, t equals 2, t equals 3, I get random circuits. Okay? So I have the first property. So I can run the algorithm, approximation algorithm for each of these c primes, and they look random, it's going to give me an answer. Now, how do I put the answers back together? The idea is to use interpolation. So if you do a Taylor expansion of this gate, then this probability here is going to be some polynomial that in t of quantities that are related to the original, to the output probability of the original circuit. And here I'm being a little bit vague, but by doing this Taylor expansion and doing interpolation, you can recover the value of the original circuit C by having these values for different t's and then interpolating to recover the value of this at t equals 0, which is the value that you really care about.
You're talking about the precision of H.
No, the precision of H? No.
Okay.
It's
So
just
it would
like a
be
random
any
H.
number between 0 and 1.
No, H is a matrix. So this is,
Yes,
I'm sorry,
the
yeah,
eigenvalue of H.
yeah.
The eigenvalue of H would be any.
No, it should be general, it should be random, yeah.
So any number.
It should be a generator, you know, if I choose like a very specific H, if I choose H to be the identity or something, it's not going to work. Like it should be generic enough. No, they're not the same, I'm sorry. So let's call this T, capital T, and this, let's call this capital T. And then I set T equals to 1, to 2, to T, and I get these circuits, C prime 1, C prime T. Yeah. Yeah?
You say it's very hard. He's the worst case. I would assume you want to show me that you can solve an arbitrary case. Not given I know the worst case, I would be able to.
I'm showing you how to solve an arbitrary case. So this is the arbitrary case. I'm explaining how you solve it. So you start with the arbitrary case. Okay, I'm assuming it's a single qubit circuit, but you could generalize that.
You don't care right now it's the worst case. You're saying it's
Arbitrary, sure, arbitrary. Yeah, exactly. Yeah. This is, you need that to be able to do the interpolation. No, I mean, if it's a many qubit circuit, there'll be a different H for each gate. So each gate will be followed by some random thing like this with a different H per gate.
So just one layer of single qubit gate.
No, if it's a 2 qubit gate, you put 2 qubit gates.
So calculation equals 2.
Yes, so there's a very technical argument there, which is actually the main gap currently in all these arguments, which is that it doesn't work for factor 2 approximations. If I have factor 2 approximations to the C primes, this is not enough to interpolate. If anyone has worked a little bit with polynomial interpolation works very well if you know exactly the value of the polynomial at various points, and it has low degree, you can recover the value at any point. If there's a little bit of error in these values, it kind of really breaks down. And you need to work extremely hard to be able to tolerate even tiny errors in the evaluation points. Even if you can add redundancy and stuff like that, it's still extremely hard. So this argument actually only works not with factor 2, but with factor 1 plus 2 to the minus the number of gates in the circuit. That's the state of the art. M is the number of gates. So it's much weaker than what you'd want. Of the gates of the circuit, yeah. But there's many different H's, right? So if I have many different 2 qubit gates, I add a new one here, and this would be H1, U1, and then maybe there was U2 here, and I'll add H2, etc. Yeah. Yeah. You want to keep a circuit that has a similar architecture. No, you're showing that the task is hard. So arguing that it's hard to get py exactly is weaker than arguing that it's hard to get py within a factor 2. Right? So if you were actually solving it, it would be better to solve it with that. But I'm doing the opposite of solving. I'm trying to argue that it's hard. And I'm only able to argue that it's hard for that closeness. So exactly I can show, or not me, people working in this area, and that kind of approximation they can also show, where M is the number of gates. So this, okay, there's references for this coming a little bit later. Okay, so that's the first idea, and this idea gets rid of one of the main problems, which is how to boost the hardness argument from worst case instances to average case. And now we know that if we're able to succeed in the test for a random circuit C, then we know how do we, in principle, be able to use that in order to succeed for a worst case C, and then we'd be able to unwind the whole argument that I gave before to solve gap P functions, etc., sharp P functions, etc. Okay, there's a second problem that we had to deal with, which was the fact that this is not the, whether factor 2 or that kind of factor, this is not the task that the quantum computer is solving. The quantum computer, assuming it has really small levels of noise, is sampling PYs that have a small total variation distance, not that are close multiplicatively. So I'll write it again here. It was, this was our cost function, not multiplicative approximations. Okay, so we want to show that this is hard. The main idea there is to use what's called anti-concentration. So where could there be a problem? There's going to be a problem if many of the output probabilities are extremely small. Okay, suppose that many of these YC0 squared are extremely small numbers. Then getting a multiplicative approximation to very small numbers, that's very hard because you're trying to pin down something that's extremely small. Say it again? Yeah. Yeah, but there could still be, in principle, there could be many of them that are 2 to the minus 10n or even smaller. That's what I mean by smaller than exponential. On average, they're 2 to the minus n. What we need, I'll say what the statement that we need. So the statement that we need is that the probability that this value is not much smaller, I'll put some constants, but let's say it's not much smaller than 2 to the n. So let's say less than 100 times 1 over 2 to the n. This is at least, don't trust my 1 over hundreds, I'm just writing them for concreteness, but you need that some noticeable fraction of these output probabilities need to be larger than some fraction of the average. So this is what you need. Yes, then this holds. No, there's not that many for the exponential distribution. So the tail is not that, it doesn't go that down. So it's not, 1 by 100, it's not that much, right? I'm not saying that almost all of them, there can still be 99% that are very small, but for the argument to go through, that's enough. So you can show that the exponential distribution satisfies this, and you can also show that the output distribution of these random circuits satisfies that. That's a little bit more work. Once you've shown that it satisfies that, which is probably known as anti-concentration, then you can relate, and I'm not doing it because I don't have time, you can relate this cost function to the multiplicative one. And you can show that if you've argued that multiplicative approximations are hard, then these approximations are also going to be hard. There's a gap. So it only works if you've been able to show that the multiplicative approximations are hard up to a factor 2 to the minus n, where n is the number of qubits. It needs to be hard for this, and then there's no gap. Everything is fine. We could only, this is what I said, we could only show that it's hard, or let's say, yeah, okay, let's see, to 2 to the minus m. M is the number of gates. Okay, in general, there's more gates than qubits. So this number is closer to 1 than that number. So this is a harder task. And I've only shown that this is hard, but not that. And so here, the moment the arguments just break down. They just break down. So it's not finished. Yeah, so let's get to the bottom line soon. I'll just summarize the argument and then give some conclusions, and then we'll be at the end of the lecture. These are references if anyone wants to learn more about how these things are proven. So let's summarize, and then I'll discuss the bottom line. Okay, so I wrote a summary of how the argument goes because I know that it's a little bit hard to follow where we're standing, so I try to explain here. So we're trying to argue that the first blue box at the top left is impossible, okay? We're trying to argue that there is no classical algorithm that samples from the correct output distribution even within error epsilon in statistical or total variation distance, and we're trying to show this for circuit C that's randomly chosen, okay? We want to show this is impossible. Okay, the first step is to reduce that task to a task that looks harder, but we argue that it's no harder. So we can show, using anti-concentration, that if there was a classical algorithm of the first kind, then there's actually a classical algorithm that samples from the same distribution, but now with multiplicative error. The multiplicative error is 1 plus 2 to the minus n. N is the number of qubits for a random C. Okay? So if the distribution is anti-concentrated, which it is, if you can sample with error epsilon and total variation distance, in fact, you can also sample from the correct distribution just with multiplicative error. Okay. Now we want to get rid of the random C part. For this, we use the interpolation argument that I described. We can show that if there's an algorithm that works for a random C, in fact, there's an algorithm that samples from the output distributions with the same error for any C, including worst case C. This is using interpolation, but there's a gap here because this interpolation argument, the best that's known at the moment, it only works for approximations that are more stringent than the ones that we're trying to rule out, okay? So if you want to be able to complete the path, you need to take epsilon to be exponentially small. And then again, you're like, okay, but no one does this for exponentially small epsilon. But let's accept that gap, let's continue. The last step is to argue that the bottom right box is hard. And this is this argument with sharp P functions and gap P functions that I described earlier. If there was a classical algorithm that samples from this distribution with very close multiplicative error for worst case C, then we would be able not to sample from that distribution, but we'd be able to compute the outputs of this distribution. And because these probabilities are described by gap P functions, then the complexity theory comes in. This is worst case, it's computing functions. We have arguments for complexity theory that this should be a hard problem, unless this polynomial hierarchy collapses. Okay? So that's the path that we took. I can conclude, or yeah, okay. We started late, right? So, okay. So I want to discuss where this leaves us in a way, and then there's another lecture, remember? So we'll talk about some more things. All right. So what are some things that I didn't discuss explicitly? One of the big problems is what actually is the noise level in the experiment. So in order to achieve this error of epsilon in the output distribution, you need a total noise at the end of your circuit to be epsilon in trace norm. So the amount of the trace distance between the output state of the circuit and the ideal state should be at most epsilon. In order to achieve that, the noise per gate should be something like epsilon times m, the number of gates, okay? Because every time you apply a gate, there's going to be some noise, and this noise adds up. And so if you want a total noise epsilon, and you're doing m gates, the noise per gate should be epsilon over m. So if the number of gates is 400, then this is 0.1 divided by 400. Any experiment has more noise than that. So in fact, for the task that I described, we don't even have like concrete completeness. The experiment doesn't achieve the thing that I'm trying to argue is hard. In fact, I wrote, so the actual fidelity in the Google experiment is 0.02, where 1 is good, right? So 0.02 is like, okay. And so this is why okay. And in fact, and I didn't have time to discuss that, unfortunately, but this year, just a few months ago, there is a paper that shows that if your rate of noise is not, doesn't scale with the number of gates, but instead it's some, let's say, epsilon prime per qubit, so a constant, then there is a classical algorithm that samples from a distribution that's extremely close to the output distribution of the noisy circuit. So circuits that have...
Find the 2% fidelity, that fidelity per gate, rather than...
No, so actually I can't, because it's not quite fidelity, it's something even weaker, so they don't even achieve that, but the way I would define it is just the fidelity between a whole ideal, which is the output state of the ideal implementation of the circuit, and whole real, which is the state that's been created in the experiment. So this fidelity in general is a number between 0 and 1. If the two states are equal, it's 1, and here it's 0.02.
But it's like a scalar product between them, or what?
The definition of fidelity. Yeah, it has a little bit of a complicated formula. It's the fidelity between two states is, it's some kind of inner product. If they're pure states, it's the inner product. Let's just say that, yeah. So yeah, that's good intuition if, right. So it's the overlap between the ideal and the real is just 0.02, so it's pretty small. No, 0.0, yeah, 2%.
Per gate, or is the overall?
No, that's the overall fidelity. No, per gate it's good. I don't know what it is, but per gate it's like 99 or something like this, but there's many gates, so that's the problem.
Percent probability to get the exact right state or not?
No, I mean, not really. It means they get a state that has overlap 2%, but there's no chance they get the exact right state. It's, yeah.
Is the random choice in half? You get your half?
No, it gives 0, because for a random state, you have a target state, you take a random state, it's going to be orthogonal as soon as the dimensions are higher. So this is another high dimensional phenomenon. Okay, you can thank me, but I feel I'll just still make my second point, which is that because this is what's going to be addressed in the next lecture, we have a problem with verification, and I didn't really discuss it, but how do you check this? You'd have to compute these numbers. That takes an exponential amount of time. We're actually arguing that it's hard to compute these numbers. And you'd have to estimate these numbers. You'd have to do exponentially many experiments to estimate this. So you can't compute this, you can't estimate this. This is why in the actual experiment they use a proxy, they don't compute this, they use a target function that's a little bit easier to compute. I mean, actually it's still exponentially hard to compute, but at least it doesn't require exponentially many samples to estimate. And this is why they can do the experiment with 10 million samples, which is not at all exponential in 53. It's much smaller. But it's cutting a corner, and then people can leverage that in order to find also efficient classical algorithms. So that's a second drawback. Okay, so first drawback is that this is actually not really a noise-resistant experiment in the sense that the hardness arguments only apply for a very small number of noise. The second drawback is that verification is actually very hard. And the third drawback is that there's not really any applications. I mean, it's hard to build on this kind of an experiment. You do it and then so I'll try to address some of these in the next lecture. Okay, now I stop. Thanks. You don't need to clap again.
So, estimating this sum, this is hard on a classical computer or also on a quantum computer?
Which one?
This one on the top.
Yeah, it's also hard on the quantum computer. Yeah. I mean, estimating this number is hard on a quantum computer too. Because you can run the circuit and you'll get some y, but you got to do that random. If you have a y in mind and you want to know what's the probability that my circuit is going to return that y, there's no quantum algorithm for that. In fact, that's a gap P complete problem, so there's almost provably no algorithm for that, classical or quantum. Yeah.
So why is it important to have a finite fraction of probabilities greater than 100%?
It's to relate it's just to argue that succeeding in this task, so by succeeding in this task, I mean coming up with a randomized algorithm that returns y with probability py that satisfies this function. I want to argue that this is hard, but the only thing I had managed to argue before is that finding a classical randomized algorithm that returns y with probability that's within a factor 2 of this, that's what was hard. And to go from the one to the other, you need that. Yeah, you can relax these things quite a bit. Yeah, if it's an inverse polynomial fraction, that's fine. Yeah. Yeah, these factor 2s, they were just for purpose of exposition, but you can make them, there's a lot of wiggle room. Yeah, that's fine. That's fine.
Can you elaborate one more time on the noise per gate versus the noise per qubit?
Yes, so this is our target function, and I'd like to be able to do an experiment that succeeds in that target function. Now, how much noise per gate should my experiment have in order to succeed? And the argument was, well, this allows epsilon, think epsilon 0.1 gate noise in total. So each of my gates, how much noise can it have so that in total I get epsilon? Well, the noise per gate should be epsilon by the number of gates. And so in total I get epsilon. So this is my target. In order to get an experiment that succeeds in this function, this is the noise per gate I need to have. Now, how much noise per gate does the Google experiment have? Well, it's some number, right? And that number is, some other number divided by m. So you can, because it's not asymptotic, you can always argue. But I think the kind of expectation from experiments is that currently the noise per gate is a constant. It's like 1% or 0.1% noise per gate. And the number of gates, which was 400, is definitely bigger. The noise per gate is not 1 by 400. It's something bigger. So they don't achieve this target, so they don't succeed in this metric. They succeed in some other metric that they introduced, but then after the experiment, there were a number of papers that show that actually for that other metric, you can succeed using classical randomized algorithms. The only one we can show is hard is this one, and even there, I said that there's a gap in the arguments, right? So